Hello, everybody. Thank you for joining us for our fourth Weiler Wednesday webinar. My name is Nate Schmidt. I'm the Director of Marketing with Weiler Abrasives. And today we're switching gears a little bit. We've been covering a lot of topics around metal fabrication on our first three webinars. This week we're switching gears to what we call industrial production, and more specifically high volume production that we'll cover on the call today. Again, our topic is automated deburring basics. And I have Rick Sawyer joining us. He's our Technical Business Development Manager, and he's going to go through the presentation today. Before we jump into it, just a couple tips on Zoom. So as I said before, everyone's line has been muted just to prevent any background noise. However, we will take questions and answers through the Q&A function at the bottom of the Zoom screen. So at any time throughout the webinar, feel free to pose a question in there, and we'll answer those questions at the end of the webinar. In addition, we'll have a contest about halfway through the webinar. You'll have a chance to win a prize, and we'll ask that you submit your response through the chat function. So at the bottom of your screen, you should see a chat button. You'll submit your response to that question through chat. And then lastly, we'll do a poll during the webinar, and you'll see that pop up on your screen, and we'd appreciate your participation in the poll. As a way to get some interaction from the audience throughout the webinar. Before we dive into it, just a quick couple words on our response to COVID-19. Obviously, it's a challenging time for all of us. We want you to know that our factories around the world continue to operate, and we've been deemed an essential business, mainly because we support customers like yourselves in mission-critical industries, like the one shown on the screen here, shipbuilding just being one of the many industries that we continue to serve. And I want to thank our coworkers that go into our factories every day. We've taken many precautionary measures, including wearing masks, the social distancing, sanitizing, and other measures to keep our coworkers safe. But really, without those coworkers that are going into our factories every day to produce the products that we need to keep running, we wouldn't be here. So thank you to those folks that go in every day on our factory floors. If you guys are looking to get any additional information on our response or our status as a business, you can find that on our website at weilerabrasives.com. I also encourage you to join our social media channels, LinkedIn, Instagram, and Facebook to get the most up-to-date news. So without further ado, I'm going to turn it over to Rick. Take it away, Rick.
Thanks, Nate. Good afternoon, everyone. Today we'll discuss how to replace existing edge prep processes currently being done manually with an operator by moving them into an automated process utilizing abrasive nylon filament brushes. We've also provided some do's and don'ts to help make your deburr automation process successful as well as cost effective. Automated deburring. Automated deburring has really grown in the last 10 years. So what opened the door? Equipment advances like 60,000 RPM spindles and very effective cutter coatings have minimized burr sizes, meaning burrs can now be removed with compliant media. Some of the types of automation that you should be looking at are in-machine CNC deburring, where the part is fixtured in the same fixture where it's machined, robotic deburr cells that could either carry the media or carry the part, or a custom-built deburr machine. That's typically in a high-volume production application where you have little tool changeovers. What does automated deburring give us? Reduced direct labor content, increased throughput, media cost reductions, part quality improvements, and minimizes ergonomic and safety issues. Some of the high volume industries to look for deburring opportunities are aerospace, automotive, medical, and aluminum castings. Many years ago, Weiler developed their own burr classification system. The reason for this is if somebody called from aerospace and said, hey, I have a small burr, you know what? They probably had a small burr. Then a gentleman that built skyscrapers would call and says, hey, I have a small burr. Typically, that was not a small burr. So we developed this system to quantify the burr size so it would lead us to the appropriate media for the application. If you look at the burr classification system, there's 5 classes. Class 1 is really no burr. Maybe it's a Blanchard ground part or double disc ground part, and it's really got sharp edges but no visible burr. Class 2, the burrs are visible, but they're easily removed. Maybe we could just flick it off. You get to class 3, the burrs are still kind of small, but now all of a sudden the root thickness or their attachment point is starting to grow, and it's going to take some energy to remove it. Class 4 is now starting to move away from surface conditioning or compliant media. Wire brushes is still capable of doing it, but we need a lot of speed and a lot of impact. That's how that's going to remove it. Class 5, in my eyes, that's parent material. That's not really a burr, and that needs to be cut off or ground off. None of the compliant medias are going to be capable of removing it. Some of the common deburring application: edge deburring, where I need to remove the burr, but not necessarily at a radius. Bore deburring and finishing can be straight plunge. However, if you interpolate, you're going to get more parts per brush. Surface finishing and deburring. Now, not only do we need to deburr, but we need to impart a finish for some function. Maybe it's oil retention or something like that. And then edge radiusing, where we need to remove the burr, but also generate a very specific edge radius, similar to what you'd see in a turbine blade. How do I choose the correct brush for my deburring process? After burr size, the next thing to consider is material and part geometry. Also, if there's existing equipment, then its limitations need to be considered as well. Wire and NAF brushes, which are nylon abrasive filament, come in very similar brush configurations. However, when compared to wire, a NAF brush's claim to fame is compliancy. By compliancy, I'm referring to a media's ability to deburr without changing a part dimensionally, particularly when a part has changes in geometry. This makes automation programming easier because you do not need to trace the part's edges exactly. At Weiler, our trade name for nylon filament abrasive is Nylox. Here are the three most common types of grains that you'll see. Aluminum oxide is the least aggressive because of its blocky grain. Silicon carbide used to be used for deburring in the past, but now with the invention and the advancements of ceramic grain, they offer a much higher cut rate. Just an FYI, everybody's aluminum oxide, no matter who the brush manufacturer is, will probably be reddish brown. Everybody's silicon carbide will probably be bluish gray. But when you get to ceramic, it's flavor of the month. Ours is black, but there's a red, there's a blue, there's a light blue, there's an orange. So there are plenty of them out there, and I'm assuming that's some marketing person coming up with that great idea. Sorry, Nate. So our black ceramic filament is called Burr RX. That's the line of product. The advantages of Burr RX are higher cut rates. These are a result of the grain's technology regarding its hardness and shape, which exposes more cutting points when extruded. As you can see from the slide, our internal testing shows that versus silicon carbide, which always did the deburring processes in the past, we get about a 4-to-1 cut ratio. What's this mean? It means shorter cycle times or larger edge break in existing application, but more importantly, now with some of the tougher materials, we can get the edge break required in the time that before we couldn't even look at the application. Nylox wheel brushes are where more total aggression or targeted focus brushing action is required. Keep in mind, Nylox brushes require a depth of interference, meaning the workpiece needs to be pushed into the brush face by a certain amount. We want the filament to drag over the edge and file the burr away. This is why Nylox brushes do not normally lend themselves to manual deburr processes. Wheel brushes will give you a focused aggression. Obviously, wheel brushes are used in bore finishing and deburring. I want to speak to the comment at the bottom. Deburring in lathes with wheels is a great application, but you need to have live tooling. If you do not have live tooling, the media will flat spot, requiring an operator to go in and keep indexing the media. And you also lose some of your aggression. The best deburring in a lathe with live tooling is to have both the piece rotating and the brush. Nylox disc brushes, now we're looking at more flatter surfaces, not the geometry height changes. One of the things you'll see here, it talks about finishing, and we're going to see that on the slide in the future. But I want to speak to the blending of light tool marks after machining and grinding. Many times end users have come back to me and said, it's not working. And when I asked, they're not blending the tool marks. They've run the milling cutter back and forth across the surface maybe 5 or 6 times. And there's a mismatch of 5 or 10 thousandths. This is a surface conditioning tool. This is not capable of blending that out. When do I use a wheel? When do I use a disc? If I use the wheel, if you look at the photo on the left, I would have to make multiple passes for that wheel to get all the surfaces. The goal here is to keep the filament as perpendicular to the edge being deburred as possible. Now, it doesn't have to be 90 degrees, but it can't be parallel. It's got to be as perpendicular as possible. So if I were to use a wheel brush for the part on the left, I'd have to make 4 different passes, or 2 different passes and then 2 different rotations to get it even anywhere near uniformly. Now, obviously, if this was an automated setup and a dedicated setup, I could be rotating the part while I brush with a wheel, and that would help the situation. However, if you look to the right, because a disc brush is used with a rotational action across the part face, now I can deburr in all directions. So if the part is flat, that would be the preferred method.
All right, like I said, we've got a webinar giveaway here. We're going to be giving away another one of our Weiler power packs for charging your mobile devices. And we're going to pose a question here in just a second. Again, the first person to answer in the chat function within Zoom will win this power pack, and we'll get it out to you, and we'll announce the winner at the end of the webinar. So the question is, what color is the Weiler Nylox Burr RX ceramic filament? And Rick, I appreciate your joke there. Some marketing person probably came up with those different colors.
Sorry, Nate, I didn't give that to you in our practice run.
All right, so I'll hand it back over to you again. We'll announce the winner at the end of the webinar.
Thanks, Nate. All right, let's talk about a couple things to look for and how to optimize your automated processes. One of the very first things, or the biggest concerns, is the upstream processes feeding it. As soon as you go to automation, anything that varies in a prior operation is going to come to light. For example, if you rely on your machine operators to change your cutters or your grinding wheels, instead of doing it at a part count, that is going to show up the minute you start to automate. Right? You will be setting up a process capable of deburring a specific range of burr size. It is not an operator who can say, oh, the cutter was dull and I need to run twice as long. So I refer to this as window in, window out. Any of my customers that have dealt with me for a while, any of the end users, know this saying. What comes into your process is what's going to go out of your process. Again, you're set up for a certain range of burr. If you let things get out of control, as you can see by this photo, on the left, the cutter needed to change, actually the cutting program needed to be changed. So on the right, what came out of that system was still burred, as you can see right at the upper right side of it, because the process was not set up to take that thick of a burr away. A couple things to look at. Part fixturing, as well as part geometry, is going to pose some issues. Right? If you look at this upper photo, this particular part, we needed to deburr the slots, and there's a lip sticks up on the part. So if you look at the radiuses, you see a lot of shine. That means we've got edge break on there. But if you look at the straight closest to the lip, you don't see the shine, meaning we didn't get enough edge break, and we may not even removed all the burr. It's the same issue with your fixture. I know a lot of the materials, and people just want to get parts out by the gobs, right? So you machine as fast as you can, meaning your fixtures are pretty rigid, and you come up to within 5 or 10 thousandths to the top of the part where the surface is being machined. Now I take a media that needs to reach over the side of the part by 60 to 100 thousandths, and all I'm hitting is fixture, meaning I can't deburr where the fixture is. The other thing you want to be aware of, we call this a brush, but it's truly an abrasive. It comes in a grit size. So when you look at the lower photo, when we run a disc brush across the surface to deburr the edges, we of course are impacting the surface finish. Now again, this is a surface conditioning tool, so I'm not changing your part dimensionally, but I am changing your surface finish. Say that finish was a 32 RA when I started, it'll probably be 30, 29 RA when I'm done, and that's very dependent on whatever the base material is. The other thing is, if you have very deep scratches from your cutters, we're going to leave a secondary scratch. So it'll look like the surface finish is worse, but when you measure it, it's actually been improved again because we started to blend the peaks. A couple of tips to look for. As I mentioned before, You need to present your filament as perpendicular to your work edge as possible. And again, it doesn't have to be 90, but again, it can't be parallel. Surface speeds, 2,000 to 2,500 surface feet per minute. And there's a couple of reasons for that. First reason is, remember, we're carrying abrasive grain with nylon filament. Abrasive grain generates heat. Nylon does not like heat. Next thing you know, you have what we call nylon transfer or melting onto your part. So that's one of the issues. The other issue is this product works by wiping and filing. I need to drag across the edge so that flexible file can remove the burr and generate an edge break. If I start running fast, and I've actually done this with video and strobes, if you start running fast, the filament bounces off the surface when it strikes. If the filament's bouncing, it's not touching. If it's not touching, it's not cutting. A couple of things you can do. Coolant allows for cheating, right? So coolant takes away the issue of transfer. It allows me to go a deeper depth of interference. Maybe it allows me to run a little bit faster. But the idea is to keep the nylon from transferring while improving the finish. However, if you have coolant, you need to have a filtration system. And it's not necessarily for the abrasive grain. When that abrasive grain releases from the nylon filament, it's actually bigger than some of the chips you generate from your machining operation. What the real issue is, I'm making metal dust and nylon dust, right? As the nylon breaks down, it's very, very fine dust. And on your part, it's like I've taken very fine files. So if you don't have filtration, your coolant eventually becomes sludge. Reversing spindle promotes even wear. And what I'm referring to there is if I run a wheel brush or a disc brush only in one rotational direction, the end of the filament gets what I refer to as feathered. Imagine looking at the blade of a pocket knife and how it comes down to a point. Again, remember, this is an abrasive. It works on pressure. So if I let the filament get feathered, I lose some of my pressure, I lose some of my cut rate. So in the cases where you don't reverse, you'll notice when you first put the brush on and the filaments are square, you get a little more edge break than after it's run. If you're able to reverse, which a lot of times can or cannot be, if you're able to reverse, it leaves the filament bullet-nosed, which keeps my pressure up. Always use the largest brush possible. Small brush, small results. What I mean by that is every filament's got grain, every grain is a cutter. To have a very successful and cost-effective system, I want as many cutters as I can get because that's what's going to do the work. However, obviously, as I have cutters and the filament wears and new cutters come up, now I have to compensate for wear. So something's got to trigger the brush after a certain number of parts or a certain length of time to index in so that we can keep our edge break uniform as it goes across. One of the other things I want to mention is it is the same 80 grit grain that you see on a coated abrasive or in a grinding wheel, but it is not capable of generating that kind of finish or that kind of work. In our case, the 80 grit's being carried by a nylon filament, so the resistance against it, it pushes against your workpiece to a certain point and it says, I can't push anymore, and it goes. When I push on a coated abrasive belt and there's a platen behind it, now it's driving the grain into the surface. It makes a much deeper cut. So a finish for an 80 grit Nylox or nylon abrasive is 25 RA or thereabouts, and an 80 grit coated abrasive belt could be over 400 RA. So even though they're the same grain, they can't apply the same amount of pressure. However, there are times you need more aggression. Increase in spindle speed will not do that, as I mentioned before. So what do? Let's reduce RPM, increase our depth of interference. Let's give that filament a little bit longer length to do the wiping and filing and get the abrasive grain on the surface. Let's use a brush with shorter trim. Remember, it's all about pressure. It's an abrasive. Shorter trim, more pressure. Increased brush diameter. All right, now I'm just getting more cutters. All right, more work done, more cutters. Reduce feed rate. Give the brush a little bit more time to do what it needs to do. Or you can change filament diameter and grit size. And lastly, you can go to rectangular filament, which instead of having a tangent point of contact on my workpiece, now I've got a flat with a lot more cutters touching, as well as a lot more stiffness. Let's talk a little bit about trim length. More importantly, let's talk about wheel density. Okay, what you're looking at are two brushes of the same diameter. The upper brush has a smaller arbor hole versus the bottom brush. What dictates in the brush world the amount of wire or filaments we can put in a brush is the arbor hole. That circumference around that arbor hole determines how many filaments we can lay in there when we're assembling the brush. So on the top brush, if you look to the right of the brush, you see the face and the density. Now keep in mind, these are the same filament, the same diameter brush. Now look at the density on the bottom brush. We got a lot more cutters, we have a lot more stiffness, but we gave up a lot of compliance. So depending on the application, that's going to lead you as to what kind of density or what kind of trim length that we need. If you look at the example to the right of the brushes, that's the pump gear. That particular application in an automated cell takes long trim. We want to be able to deburr the nose of that gear, deburr the valley of the gear without wiping out the nose of the gear. So we need a lot of trim. If we had short trim and we tried that, we'd over radius out on the nose. When you're talking disc brushes, toolpath is very important. One good thing about disc brushes is a lot of times you can use the same cutter parameters, just start reversing. So if I take the same toolpath and I reverse my cutter, what we're trying to do is not allow the burr to fall into the slots or into the holes. We're trying to pick it back up so it's easier for us to file off. The other issue is you need to start the brush off the part, come fully across your part, and come back off your part. It's not a cutter. It can't just work up to the edge. It's got to go all the way across, which brings us to number 3. The center line of the brush may need to be offset to get more filaments over the edge. By that, we mean if you look at these photos, if you look at C, the not recommended, the problem with that is I've got these filaments, which are great. They're conformable. That's why we're using them. But if I take 3 or 4 filaments and I take my finger, I can push them away pretty easy. I'm not getting any pressure, meaning I'm not getting any cut rate. So B is good. I can use the same brush, but now I'm on the center line. The problem with B takes more cycle time, takes more tack time, which is not desirable. A is the best. I've got a lot of overhang. So not only now do I have a lot of pressure, I've got a lot more cutters doing the work. That gives me better cycle time and a better cost per part in regards to media. If you're looking at automation, these are things to consider. All right. I won't go through them all, but I will say a couple of things. Robotic deburr cells allow for more immediate tool choice options and also give you the ability to perhaps regrip your part and expose areas you couldn't reach to if it was in a fixture. CNC obviously gives you the advantage of utilizing existing fixtures, existing equipment, and also have coolant. So they both have pluses and minuses, and this list that you see will help you narrow down which one's the better option for your particular project. One of the things I'd like to ask folks or tell folks, take advantage of the resources available to you. The Weiler Process Solution team is here to serve you via phone, lab processing, on-site visits if required. Also, our website is full of resource guides, such as the automated deburring brochure, which I'm a big fan of. If you contact me, you get it automatically, which will give you some of the starting points regarding depth of interference, RPM, feed rates, and so forth.